This video is about creating beautiful figures for research papers. We will walk through the whole process of creating high-quality figures using popular programming languages like Python and Julia. We'll explore how small design choices like fonts, colors, and layout can make a big difference. Finally, we'll see how these figures look like when placed in real manuscripts. Hi everyone, my name is Andrey. I'm a researcher at Imperial College London. I know you've been waiting for a long time for this second tutorial on how to create beautiful figures for research papers. And I'm sorry it took me almost 6 months to produce this second video. I was quite busy with my research projects at Imperial, but now I'm finally back and I'm making this new tutorial where I will show you the whole process of creating beautiful figures, starting from coding in programming languages, then adjusting the figures, and then finally placing them in real manuscripts. To share these examples with you, I've prepared a GitHub repository called Beautiful Figures. This is what the repository looks like. I describe the problem of creating beautiful figures and show one example here, and then I list the principles of beautiful figures that we discussed in the previous video, so you can see the link to this tutorial here. Then I have 2 folders with code examples for Julia and Python, and today actually we will consider these examples. We will try to create not a very beautiful figure, then we will tune several parameters and create a beautiful figure. And we will also discuss multiple aspects of plotting, including color schemes, layout, etc. So please feel free to check out this repository, github.com Andrey Churkin Beautiful Figures. And hopefully it will inspire you to use more parameters when producing figures. And here is an example of a manuscript that I created for this video. You may see this is mostly an empty manuscript following the IEEE Transactions Journal 2-column template. Then on page 2, I have here 2 empty figures, and our goal for today will be to replace these figures with something else, with our data visualization. And then we will be able to compare how different figures look like in a realistic manuscript. When developing figures today, I will be following the design principles that we've discussed in the first part of this tutorial. So if you haven't watched it yet, please click on this link and check it out. By the way, I have an idea of developing a dedicated professional course about data visualization and graphics. Such a course may be useful not only for creating figures for papers, but also for people outside academia, for anyone who is interested in data visualization. This course will be much more detailed than YouTube videos. It will have multiple modules covering theoretical aspects and practical applications. I will also develop homework assignments for you and provide some feedback and mentoring. Please let me know in the comments if you are interested in such a course and what are the most critical challenges and problems that you would like me to cover. I would really appreciate your feedback and I would really like to know your needs and your problems in data visualization. All right, now let's talk about the process of creating beautiful figures. And to make this tutorial more structured, I have divided this process into 4 stages. And the first stage is to create a figure in a programming language. So you have your data set and you need some tool to start plotting it. The simplest tool is of course Excel, but we will not cover Excel today because it's not really good for scientific purposes. So usually you will need to use some visualization libraries in languages like MATLAB, Python, R, Julia, etc. And in these languages, you will need to tune multiple plotting parameters to get the desired outcome. So this is the first stage when you just prepare your data in a programming language and you visualize it. Then the second stage involves graphics software. The point is that the figure that you just visualized in, let's say, Python may still be not ideal, and you may need to tune some parts of it or modify it further to make it publication ready. And here we will discuss the use of vector graphics software. There are several popular software like Adobe Illustrator, CorelDRAW, and Inkscape. You may try to use all of them. I would just say that Adobe Illustrator and CorelDRAW are the most powerful ones and the most user-friendly, but the problem is that they are not free, and you may need to apply for a free trial period, or maybe you will need to buy it. If you don't want to pay for such graphic software, please use Inkscape. I know that it's really popular nowadays among students, and it can perform most of the operations, most of the adjustments that you may need for your figures. Then stage 3 is to place your figures into a manuscript, let's say in LaTeX overleaf. The point is that even if you like your figures produced by a plotting library, they may not look ideal in a realistic journal template, let's say in this 2-column format. Some figures may be reduced in size, the colors may change, the readability may be reduced, and we need to test all of that. Then step 4 is to repeat. If you don't like how your figure looks like in a real manuscript, then we need to repeat the previous steps. We need to maybe change our code to adjust some elements of the figures, or maybe we need to modify some parts of the figures using vector graphics software. So this is the overall structure of the design process that I'm following. I'm coding my figures, visualizing my data, then I use vector graphics software to further modify the figure, then I place it in a real manuscript, and then I repeat the process if I don't like the final result. Now let's talk about step number 1, coding and plotting your data. And I believe that this is the most difficult and tricky step of data visualization, because you literally have empty file and you need to run your code and you need to visualize your data from scratch. And while doing so, while working with plotting libraries, you may tune hundreds of plotting parameters. And this is very confusing because you simply don't know which parameters would work better. And you may spend days and days tuning these plotting parameters to produce an effective data visualization. And if you don't tune these parameters, as we will see today, your figures may look somewhat ugly and ineffective. What are we going to visualize today? I decided to visualize a very famous and simple data called iris flower dataset. And this dataset has 3 subsets corresponding to 3 flowers: Iris setosa, Iris virginica, and Iris versicolor. And for each of these species, we will be showing the length and width of different parts of the flower, as you can see in this picture. So that's it. This will be a simple goal for today's video. Let's visualize this dataset, let's create this simple figure, but let's try to follow all the design principles and let's try to make it beautiful and effective. Now I will show you my screen, my code editor. We will produce a figure of this dataset together and then we will discuss if we like it or not. This is my VS Code editor, and I opened here a folder with this code repository called Beautiful Figures. And today we will be coding in Python because I believe that this is the most popular language among students and researchers. But I also have some examples in Julia. So if you open this subfolder Python, you may see few examples: beautiful figure example.py and not a very beautiful figure example.py. So let's start with this figure. You can see I have some description here explaining why this script is called not a very beautiful figure. And then we start visualizing our data. And I believe that this script is quite simple and also self-sufficient, which means that you don't need any additional data. You may just run this single script and it will produce a figure for you. Let's discuss what we see here. We import a few packages: NumPy, Matplotlib. This is a visualization, a plotting library that we will use to produce our figures. And then we have this sklearn library. From this library, we will use some linear and polynomial regression functions. And also you can see that I say from datasets import load iris. This means that we are loading this famous iris dataset and we will be visualizing it. You can see below that I am reading this dataset. I am assigning some features and targets for this data, names of the features, etc. Then we select what to visualize. I call this X column and Y column. And for example, if you set it to 0 and 1, you will be visualizing sepal length of the flowers versus sepal width of the flowers. Then I want to show you example of few lines of few additional analysis, and that's why we will be calling a polynomial regression function. And here you may select the degree of the polynomial to use. So you may select degree 2, 3, or 4. And then the sklearn library will do the rest of the calculations for you, and we will be able to visualize our polynomial regressions. Then remember that we have 3 flowers: setosa, versicolor, and virginica. And here I say select the datasets to visualize. So let's say that this list datasets to plot will have only 2 flowers, setosa and virginica. We will visualize only 2 subsets. And that's it. Our data is ready to be visualized, and that's why here I say let's create a plot. So I'm using this command plt.subplots. And I say that this is not a very beautiful plot because we will be using all default parameters. We are not adding any additional parameters and any customization. So here the empty plot is created, and then we need to add our data, and I'm doing this in a loop for each dataset. So you can see that we are iterating over this list of flowers. I'm preparing X data to plot, Y data, and then I'm using this command scatter and giving these dimensions to produce a scatter plot. Then we calculate the linear regression and we add this to the plot using the command plot, giving the range for this linear regression and the estimated values. And the same for the polynomial regression. We calculate the polynomial regression and we add it to our plot, again using the command plot. And that's it. Then we add the legend and the simple figure is ready. Now we have to save it and show it. I'm saving it here in this format PNG. Remember that this is so-called portable network graphics, and this is a raster graphic, which means that it is not pixel-free. It has some pixels and it doesn't have any vector graphics. And as we discussed in the previous tutorial, this is not ideal for publications. But my goal here is to create a not very beautiful figure. That's why we will be saving it in PNG. So everything is ready now to create a not very beautiful figure using Python's matplotlib library. So let's click here on the Run button and see what we get. Okay, and here is the result. Here is the figure with all default parameters. Remember that we literally didn't change any parameters. We just prepared data, we just gave names to the data sets, and that's it. Now let's discuss if we like this figure. So what do you think? Do we like this figure or not? Even though I cannot say that this is an ugly or ineffective figure, I believe that it has multiple problems, and I want to discuss these problems with you. The first problem is the size of the figure. The problem is that the size may be arbitrary, it may be random, and it may depend on the data that you are visualizing. This means that your figures may be stretched differently in different dimensions depending on your data sets. And even though it's okay when you are simply visualizing data, it's not okay when you are preparing figures for your paper, because in your paper, all figures should be with similar sizes. So if you place them together, they should look similarly. It's a little bit ugly when you have figures and one figure is smaller than the next one. So we need to control the size of our figures. The next related problem is the image resolution. If we are saving this figure as a raster graphics, as PNG image, its default resolution may be quite low. I have checked that in Python's matplotlib library, the default resolution is 640 pixels by 480 pixels, and this is quite low. If you place this figure in this low resolution in your manuscript, it may look ugly and readers may see pixelated figures, which is not good. So again, we need to control the resolution of our images. Then the next problem is the default font. Usually default fonts in plotting libraries are not ideal for academic publications. Sometimes we can see fonts like Calibri or, in case of Python, Déjà Vu Sans. And I don't really like Déjà Vu Sans. I think it's not formal enough, and I would like to use more scientific fonts in my publications, which means that we will need to control this plotting parameter. Also, the font size may be too small, which will create some visibility and readability problems in a manuscript. So we also need to control that, and we need to select adequate font sizes for all elements in our figures. Similarly, we need to control the weight of lines. By default, some lines may be too thick or too thin, and this may not work well for our visualization task. Then we also need to adjust the size of markers in our figures. We need to make markers large enough so they are readable and noticeable, but we need to keep their size reasonable, otherwise they will all overlap and it will be difficult to analyze our data. The next major problem are default colors. Usually, visualization libraries have default color palettes that do not work well for our data. For example, consider this matplotlib figure. The first dataset has blue color, then the next dataset has orange color, and then we have green and red colors. First of all, I don't like blue and orange because they look like default colors from Excel. But okay, maybe it's not a major problem. But then we have green line and a red line. And if some readers don't know the context, they may think that green means good and red means some wrong data or some other problems. And we need to avoid such colors. So usually when visualizing data, we need to select our own color scheme, and we better select some minimalistic color palettes with just a few colors. And we will do this today. There may also be problems with the legend. As in this figure, the legend takes excessive space inside the figure and it is overlapping with our data. So what to do? We need to somehow optimize it. And if we simply put it outside of the plotting space, outside of the canvas, it will take a lot of precious space in our paper and it will look ugly. So some work needs to be done to optimize the placement of our legend and the elements that we want to show in the legend. And the last problem that we may face when visualizing data is a wrong order of elements. Again, consider this figure. We can see that the lines are displayed on top of our data points. Maybe that's okay, but what if the data points are more important than the lines? Then you need to place lines at the background. And to do that, again, we need to change tuning parameters when producing our figure in Python. We have now discussed all the problems of this figure and why I don't like this default visualization very much. To improve this figure, we will now fine-tune these parameters in my Python script and see step by step how we will overcome these problems and produce a beautiful and effective figure. So let's check my script called beautifulfigureexample.py. Okay, so we are back in my code editor, and now let's find and open the script beautifulfigureexample.py. In this script, the figure is built with multiple parameters, but let's discuss what we see here step by step. Again, we can see that we import the packages, the libraries, then we open our iris dataset, we select which columns to visualize, polynomial degree, etc. Everything is as was in the not very beautiful example. Then you can see that I have multiple plotting parameters commented out. This is because I switched them off for now. And we will be including them one by one, step by step, to see how we can improve our figure. So for now, we are just creating again a simple figure with default parameters. The only thing that I changed here is this. I'm saying not just subplots brackets, but I say subplots and fixed size 10 by 10 in brackets. And this command will allow us to create a square canvas, a square figure with a resolution of 1000 pixels by 1000 pixels. So we are improving the resolution a little bit. Then we are plotting again in the loop for each of the datasets, for each of the flower. We have scatter commands and plot commands. Then the legend, all of this is commented out again. And finally, we are saving our figure. But as I said, PNG raster graphics is not ideal for publications, and therefore we will be also exporting our figures as vector-based images using PDF formats and SVG formats, scalable vector graphics. I will also create this PNG figure called step, and this will help us later to analyze what steps we did to improve our visualization. So first, as I said, most of my parameters, customization, is switched off, commented out for now. Now let's just run this script and see what we get. Okay, this is the figure. You can see that the canvas, the figure became squared now, but overall this is almost the same figure that we called not a very beautiful one. The same colors and the same fonts, everything is the same. Now let's try to improve this figure step by step. And the first thing that I would like to improve here is our plotting limits, plotting range. So the most important thing here for me are these data points. but we are kind of far away from them. We also see these lines, they're quite long, and we see additional space separating the lines from the border of the plotting space. And this is not great. This happens because plotting libraries in Python or in any other language, they simply don't know what you would like to show. They see that you are adding some data points here, but they also see data points that form these lines, and they try to show everything, all elements at once. But sometimes we don't need this. Sometimes we need to see only, let's say, this part. Maybe we just need to see the data points, and then the remaining parts of the lines of the regression analysis should be simply cut off. So to do this, at the end of this script, I have this part which I call zooming out. Let's uncomment it. First of all, I create this new parameter zoom out. So far, by trial and error, I set it to 0.6, and I think this is one of the best options for this particular figure. But basically, it allows you to manually create the zooming out effect, the scaling effect when you want to show your data. Okay, so we created this zoom out. Now let's see what I'm doing. I know the data that I want to plot to show, the most important data, the data that will be serving as a reference point for zooming away from the plot. And in the loop, I create this array, all data X to plot and all data Y to plot, basically horizontal and vertical components of the data points. And you can see that here in the loop, I am adding all data that we are plotting to this new array of data points in the loop. So if we are plotting something and we believe that this is important, it should be in the figure, I simply add it as an extension to this array data X to plot and data Y to plot. Now, what I'm doing later, I'm calculating the minimum value of the X component and the maximum value. Then I say, okay, let's compute the median and the range. So basically, we want to know what is the middle point of our data that we are plotting and what is the whole range of data. Then we do the same for the Y component. We calculate the minimum value, the maximum value, median, right in the middle between min and max, and the range. And then I create this new parameter called plotting range. And plotting range is the maximum between horizontal plotting range and vertical plotting range. So I want to be fair. I want to create the same square plot equally zoomed out from the center of our figure. And plus, I am adding here this parameter zoomed out. So I am extending this plotting range, and basically I'm telling the plotting library that we will be flying further away. We will be zooming out from our data set equally in all directions. Now everything is computed, the plotting range, and we can simply set the new plotting limits. And you can see here I say set X limit and set Y limit. How are we setting the limits? We know the median, so we say median minus plotting range divided by 2. And the maximum, the upper limit is X median plus plotting range divided by 2. So the difference is that here we have minus and here plus. And we do the same for the vertical component, Y median minus plotting range divided by 2, and Y median plus plotting range divided by 2. This may seem confusing, but let me just open Paint and draw an example for you. So let's say that this is the whole data that we want to plot. What I'm doing here, I'm estimating the length of its horizontal component and then the maximum length of its vertical component. And also I know the median points, so I can find where is the center of this data set that we're visualizing. And it is somewhere here, right? Then I calculate the maximum plotting range. It is equal to this larger component. I'm adding this delta, let's say delta, which I call zoom out, and I apply the same plotting range to vertical and horizontal components. So I'm basically creating a box, a square box, which is equally zoomed out from the center of our data set. And this allows me a precise manual control over the plotting range. Okay, back to the code. Now we set the limits, we set the zoom out parameter, the new plotting range. Let me just call it step 1, so we are saving a new figure, and let's run the code. Nothing changed in the style of the figure, but we changed the limits, and now we are kind of zooming in closer to the data points. And I like how the data looks now. It's easier to analyze. We are not too far away from the data sets. Okay, now let's tune more parameters. Let's go to the beginning of the script where I create the figure. And the first thing I would like to change is the font. You may simply set the new size of your font in the figure, but there are many more parameters that you may use. For example, here I create this command params update, and I'm explicitly saying that the font family that I want to use is Courier New. To me, this is a more formal, more scientific font. I know that this is called a monospace font, and some people don't really like it, but again, this is a matter of taste. You may use any scientific, any formal font that you would like. And then you may set the font size for your entire figure or for different elements of the figure. For example, for axes, for ticks, for labels, for legend, etc. In this case, I already performed some experiments, and I know that I should better use font size 20 points in this example. And I know this because I will be working in an IEEE journal template, and that template has 2 columns. So our figure will be placed in one of the columns, and it will be reduced in size. It will not occupy the whole page, just half of the page. And then when our figure will be reduced, the 20 points will be displayed as 8 points. And 8 points is exactly what we need, because this is the smallest font allowed in IEEE transaction journals. So basically, we will be using this small but readable font to make annotations in our figure. All right, so we specified the fonts now. Let's go here and call this step number 2. And let's run the script. Here is the new result. It's the same figure, the same plotting space that we selected, but now we see new fonts. And not only it's a new style, the Courier New font, it's also much larger than in the previous version with default parameters. And as I told you, through trial and error, I know that this font will be readable in my paper. Let's continue tuning the parameters. The next thing I would like to check here are these commands. Let me uncomment them. What am I doing here? First, I set the aspect ratio of this figure to equal. So I'm trying to create a locked square shape. As I told you, it's important to control the size of your figure, so all figures in one manuscript, they are of the same size and they occupy the same space. And before that, we set the figure size 10 by 10, but here I'm also telling that the plotting space, the canvas, also should be equal. Then let's talk about grids. Before that, in the default figure, there were no grids. The space was empty. But we can add some major grids and minor grids. Minor grids meaning that there are additional grids placed between the major grids. So basically, if we activate both, we will have a lot of vertical and horizontal lines in our figure. This is actually a controversial topic because I know that some people don't like adding major grids and especially minor grids to their figures. And they believe that this makes your data visualization overly complex and you should simply remove all grids and just focus on your data. In my opinion, major grids and minor grids sometimes may work well. Sometimes readers may want to explore parts of your figure. They may want to zoom in into some parts of your data sets and see which exact values they correspond to. So I would say that in some visualizations, adding major grid and minor grid is good. Let's try to keep them in this work. But to keep the figure beautiful and professional, of course, we should not add bold black grid lines. We should make them very light and transparent. And for this purpose, I set the line width to a small number, 0.75 for major grid and 0.25 for minor grid. And also this parameter alpha, which means transparency. So all these lines, not only they are thin, they also have very light shades of gray because of their alpha transparency parameters. So major grid will have 0.25 transparency and minor grids will have alpha of 15%. Now we save the script with these new updated parameters. We also export our results as step number 3 and let's run it. This is the result. The difference from the previous step is that we have grid lines. And even though we have a lot of grid lines, major grids and minor grids, we set this alpha parameter and the thickness to very low values. That's why it's not disturbing us. It's not interfering with our data. And I believe that this kind of grid visualization may be quite effective in scientific papers. Let's keep tuning the parameters. The next thing I would like to work with are colors. You can see here that I say, now let's work with the colors, and we need to select an interesting and effective color scheme for our visualization. So for this work, I found this interesting color palette on my favorite website, colorhex.com. Let's check it out. If you use this link, you can see that this is a so-called purple teal tones color palette, and it has 5 colors inside, ranging from light purple to dark purple to light teal and then dark teal. And I really like these colors. I think they're quite beautiful and minimalistic. We have only 2 distinguishable colors here, but using all these gradients, we can create really beautiful figures. And if we need to display more data, we can use some neutral colors like gray and black. So this is the color scheme that I like, and I will be using it in this project. And how to use these colors? All the hex numbers are given here, and if you need red, green, blue components, they are given here. So you need to simply copy these values to your Python code. Let's come back to the editor. You can see that I created a list here called dataset colors. Since I have 3 flowers, 3 subsets, I use 3 colors. And also I would like to set the colors of the lines of these markers, the edges of the markers. So I'm also assigning slightly darker versions of these colors here. So I created 2 lists, dataset colors and dataset line colors. And recall that we have some lines regression analysis. Before that, they were displayed in random colors like green, red, etc. Now let's use just one color, let's say this one, neutral gray. And then when plotting in the loop, we need to activate commands that control the color. For example, in the scatter plot, we can say that color for this dataset equals dataset colors plus index. Similarly, in the regression analysis, we use the regression color, and here we also use the regression color. And let's control the style of the lines as well. Let's say that if this line is polynomial regression, the line should be dashed. Okay, I saved the script. Let's call this step number 4, and let's run it. This is the new result. I would say that these new colors are much more stylish. They are working well together, and also the gray lines are more minimalistic. Note that we still understand what they mean, but we don't use these unnecessarily bright colors like red, green, and blue, etc. So we have only 2 main colors in this visualization. It becomes more minimalistic, but very effective and beautiful. Okay, let's keep working on the plotting parameters. The next thing I would like to change here is the size of the markers and the width of the lines that we use in this visualization. Maybe you noticed that in the previous visualization, the markers were a little bit small, and since we don't have many of them, we can make them a little bit larger. So I'm activating this command now. S stands for size, and I'm making them larger, size equals 90. Also, we can control the edge colors, line width, and we can do the same for the regression lines. Let's put the width to 2.6. Again, I found this parameter 2.6 through trial and error, so that the line is thick enough that it's visible, but not overly thick that it is distracting us from our visualization, from our data. Here in the polynomial regression, we also control the line width, setting it similar to the linear regression line, also 2.6. Okay, this is step number 5. Let's run the code. Now we see that the size of the markers increased indeed, and the lines become thicker. I think this is almost ready. The visualization is almost perfect because we can clearly see the data sets, the colors are working well together, and the size of the markers is noticeable, it's easily readable, and the width of the lines is also okay. So we are very close to the end. So what I don't like here, let's think about this. I think that I don't like that the lines are placed on top of data. Maybe in this case, I would like my scatter data to be placed as the first layer, and then the lines as a background. To control this, in Python, we need to use this command zorder. And this command creates an order of display. So the higher the order of a certain element, this means that it will be placed in front. And if the order is lower, this element will be placed closer to the background. So for our linear regressions, let's put Z order to 2. And for the scatter plot, for our data points, since I want to place them in front, let's put a higher Z order of 3. Again, saving the manuscript, creating step number 6, and running it. This is the figure. It's almost identical to the previous version, but now you can see that we controlled the order, and now the scatter markers, the data points, are displayed in front. And I like this in this particular example. Okay, there is one more thing missing, and this thing is the legend. For now, the legend is switched off. Remember that in the original default figure, the legend was a little bit unfortunate. It was taking a lot of space and overlapping with our data. So let's see if we can improve this. Let me just use one command here to activate the default legend. Here I say x.legend and empty brackets, so no additional parameters. Let's see what happens here. Now we see a figure with the default legend. And even though the legend is more or less okay, it's not very ugly, it still can be improved. First of all, it takes a lot of space here, and if we have additional data to plot, this will not simply work because the legend will be overlapping with our data. So it is ideal if we place our legend outside of the figure, let's say on top. But we need to do this in a smart way. And let me show you which parameters I use to control the legend. So now I am switching off a simple legend and activate these settings for a beautiful customized legend. So what I'm doing here, I'm controlling multiple parameters. I create this list called desired order, and I change the order of elements that I want to show in the legend. So first I would like to show the first data set, then second data set, and then the lines corresponding to regressions. And then I'm using this command legend to manually create the new legend in my desired order, and also I specify its location. The location will be upper center. And not only it will be in the center, I say that it will have a new anchor and it will have this new value 1.10. It means that it will be 10% higher than the box, than the plotting canvas. So it will be outside of the canvas. And also I say that the structure of the legend should have 4 columns. So I try to spread my data in the legend horizontally so it's not taking a lot of space from the paper. And also I remove the frame. I don't like when we have frames of the legend, especially if they're placed outside the canvas. Okay, let's save the script and let's run it again. Now this is the final version of the figure that I want to create today. We can see that the legend is placed on the top of the figure. It's not taking a lot of space from the paper. We like the colors, we like the thickness of the lines, the size of the markers. We also tuned the fonts, the size of the fonts, the layout. We make the figure square. We control the grid lines, etc. So I think this is the result that I will be happy with for today, for this tutorial. Now remember that we were saving our visualization steps here as Python step. Now let's just revise the steps that we did and see how we gradually improved our figure. So here I open the saved images for you, and this is Python step 0, the initial figure that we started with. The plotting range was completely wrong, and that's why we set the new plotting range and we get this. Then we changed the font. The font was too small, I should say unacceptably small for a journal paper. That's why we increase it. And also we change the font family. Then in the next version, we make the figure exactly a square with equal ratio between X and Y components, and we add major grids and minor grids. Let's compare these two figures. I think that in this case, since we don't have a lot of data to plot, minor grids help us to visualize data. So I would keep this in this particular example. Then the next step, we change the colors. We didn't like the default colors. We selected a new interesting color palette. And now we have this minimalistic figure with beautiful purple and teal colors. and light gray lines. At this step, we increase the size of the markers, we increase the width of the lines so that the data is more readable and visible. And finally, we placed a beautiful legend on the top of our figure so it's not interfering with our data. All right, so that was a long coding tutorial. We started with a not very beautiful figure with default parameters, and then step by step we were modifying plotting parameters until we liked the outcome. And now we have quite a beautiful figure in PDF format, and of course we can take it and place in our manuscript. However, before doing that, you may do one more stage, one more step, where you adjust and improve your figure using vector graphics software. I actually plan to make a separate tutorial about the use of vector graphics software for improving figures. There are so many things and features to discuss, so we can't do this in this video, but anyway, I will just show you how I'm using CorelDRAW software when improving my visualizations. So now we will open the exported figure in CorelDRAW. We will play with it a little bit, we will improve it, then we will save it in PDF again, and this final version we will place it in a manuscript and compare it with the original default figure. So let's do that. All right, so this is my folder of the code repository, and we have just created these visualization steps and the final beautiful figure python.pdf. Let's open it with CorelDRAW. When opening a vector graphics file, CorelDRAW will ask you how you would like to import the content. For example, do you want to convert all text to curves? And here you select no, because you want your text to remain text as an editable text object. And you also select here this option, maintain paragraphs, text flow and formatting. Otherwise, your figure may fall apart. Okay, so here is our vector graphics figure opened in CorelDRAW. And as I said, overall, I like it. It's very professional, very beautiful to me, but still we can improve it a little bit. And also my goal is to show you why you need vector graphics software. So just let's make a few simple modifications. First of all, I know that we have this field here. It's white and it's taking some additional space from our figure in the paper. Maybe you don't see it, but if I change the color, you can see that it is indeed a square canvas placed around the figure. So I can simply click delete and remove it. One more thing why we need vector graphics software is because we can edit any part of our figure. Let me just quickly show you what you can do. For example, if you don't like this dot here, you can just click delete and remove it. If you would like to change something about this part of data, you can select these points and change their color or size or anything else. You can also move them or delete them. Please don't use these to manipulate your data to submit some fake research results, but anyway, this is a powerful tool to make fine-tuning, fine adjustments to your data. Let's just go back. Anything you want to add here that you can't do in Python or programming languages, you can do in CorelDRAW, Inkscape or other software. For example, maybe you want to make some connections between the data sets, between some points. Maybe you want to say that this data point is somehow connected to this one. Okay, no problem. We create this spline line. We make it thicker, maybe like this. And we make an arrow. And then we can also create some description here. And we can add as many additional elements and descriptions here as we want. So we can modify, improve, adjust all elements of this figure. For now, let's delete this part. Another common problem of developing figures is that sometimes the axis description may be incorrect or it may be placed too close or too far away from the canvas space. If you want to change this, you simply select all your axis description, all these elements, and you move them. For example, you can move them a little bit down. We are not doing this in this example, but I'm just showing you the capabilities of the vector graphics software. Now, the final thing I would like to change here is the legend. Even though we worked a lot on the parameters of this legend, it is still located quite far away from the plotting space, and I don't like this large distance between the description, between the marker and, let's say, this setosa. So how can we do this? Of course, we can simply select this marker and move it here. But if we do this manually for all markers, the distance will be kind of arbitrary, and again, this may be not beautiful. Consider this example. This distance between setosa and purple is large, and teal and virginica is not large enough. And we would like to make it all equal. So we need some reference distance, and usually you can take the reference distance from your plot. For example, maybe you want to use this as a reference distance, the size of the grid line in your figure. Or maybe you would like to use this reference distance, the distance between the plotting space and the axis. Whichever you like. This is, again, the matter of taste and the matter of your design choices. As you can see here, this is a tip for developing figures. I'm creating here a rectangle just to measure some distances. And then I can copy this rectangle. I can rotate it, copy it again, and I can use it as a reference to locate some other elements of the figure. For example, if we rotate it and place like this, we can say that this is the distance that we should follow when placing the legend. Okay, great. Now let's use it to place the equal distance between the markers and the names of the data sets in our legend. So how we can do this? Again, we copy this rectangle. We copy it here, and here, and here. And now we simply manually adjust the positions of the markers. If you want, you can use arrows on your keyboard to do that. And we place this teal marker with the same distance, and this marker as well. Okay, now we need distance between different entries of the legend. So again, let's use our reference distance, and let's say that we want to use double of this distance to make the gap between the entries. So I'm pressing Ctrl, I'm extending this distance, maybe 2 times or maybe 3 times, let's say 3 times. And this will be the distance between different entries of the legend. So you can see how many additional things I created simply to allocate the elements of the legend. Okay, so let's put linear regression with the same distance as well. Now virginica. And now setosa. Okay, now all the elements have similar gaps between the marker and the name of the dataset, and same gaps between different entries. We don't need these boxes anymore. Let's just delete all of them. You can, by the way, select them like this using Shift or Alt on your keyboard. Delete and delete this. And finally, let's group them. So I say group. Now this is not separate objects anymore, but a single group. And we need to understand where to place this. So let's place it right in the center above this canvas. So what I'm doing, I'm selecting the center of this group, and I'm looking for the center here. And you can see now it clicked, it says this is the midpoint. Okay, great, we found the midpoint. Now let's put it on this line. Like this. Ready? And we don't need this block anymore, so let's just delete it. Okay, this is the figure. We made a few adjustments, we played with the legend, and now I believe it's ready. If you want to change anything else, please spend time and improve the figure, but for this tutorial, let's say that it is ready. So what we are doing now, we are selecting everything, all elements of this figure, and we say export the figure. Now I need to select the format. Let's say that we first save it as SVG, Scalable Vector Graphics, and here I say selected only. Selected only means that we will save not the entire page, but only these elements, only the figure that we need. It says that this file already exists because I experimented with this tutorial. I replace it. Ready. And let's save it in another format, in PDF as well. So let's say example for YouTube, PDF. Yes, again, selected only, the format and the name is correct. And we are replacing the figure that I had before that. Ready. Now we have these figures, and now let's place them in the manuscript. This is the manuscript template that I'm using for this tutorial in LaTeX Overleaf. It is following the official IEEE journal 2-column style, and you can see we have here the first figure called Not a Very Beautiful Visualization, and then figure number 2, Beautiful Visualization of the Iris Flower dataset. Let's replace these empty gray figures with our new figures. So for the first one, you can see that I say include graphics empty figure. We don't need it anymore. Let's replace it with our not very beautiful figure python.png. You remember this is the raster graphics that we created at the beginning of this tutorial. And now here, again, we are commenting out the empty figure, and we are adding this example for YouTube Python. And by the way, I should upload this example here first. So I am uploading this PDF. Let me show you. I'm selecting this file example for YouTube Python. It's asking if I want to overwrite. Yes. Ready. And now let's recompile our paper. All right. So this is the final outcome of this tutorial. We see two figures in one manuscript. On the left, figure created in Python's matplotlib library with all default parameters. And we discussed that this is not the best way of preparing figures for manuscripts. Many things are wrong here. The size of the font may be a little bit too small, the colors are not working well with data, etc. And then on the right, the same figure, but with multiple parameters tuned, and then post-processing in CorelDRAW, where we created this beautiful and very compact legend. And I believe that now the differences between the figures become obvious. Our new figure with customization occupies much larger space and the data is better visible. And also we use less colors, so it is minimalistic, but yet effective, and readers can easily see different datasets and different parts of the figure. When I have time, I plan to write this manuscript and I plan to publish it, and it will complement the YouTube videos that I'm doing now and the code repository. So my plan is to once again explain all these steps and show how we go from less beautiful figures to more beautiful, minimalistic and professional figures. And by the way, I will make more tutorials. I plan to add more complex figures, different visualization techniques, etc. So together we will complete this manuscript later. As I mentioned, I'm sharing all codes in this repository. So here, if you click on Python, you can see the same thing. You can see this not very beautiful figure. Then I discuss which parameters we have changed, and we get this figure. And also I talk about the importance of colors. You can see here the comparison in the manuscript, etc. I did the same test in Julia. It looks almost the same. The only difference is that in Julia, when you plot with default parameters, you get this figure. It's quite different from default matplotlib, but again, I think this visualization has some problems and we need to solve them. And then when I adjust the parameters, I get something like this, which resembles our outcome that we got in Python's matplotlib. So please feel free to check out this code repository, and I hope that these examples will inspire you to tune more plotting parameters when developing figures. Before concluding the tutorial, let me show you one more thing to demonstrate the power of CorelDRAW and other vector graphics software. And this trick is called, you can open your own paper in this vector graphics software. You can open your own paper and edit it. So I just showed you the manuscript that we created, and now I'm opening this PDF in CorelDRAW. And we go to page 2 and we see our figures. We can see that this figure indeed is raster image, it has pixels, and this figure is of infinite quality. It is a scalable graphics. Now, why do we need it? We may need it for some final checks and some final adjustments for our publications. And I will just show you one tip here, how you can check that the font size in your figure is readable. For example, here we see this figure 2. Let's create a text and let's write figure 2, fig.2, and let's say that this was 8 points, because I know that in the official IEEE journal template, this text should be 8 points. So now I go here, I say that let's make this text 8 points, and let's change it to Times New Roman, because this is the font of the journal. And let's try to compare these two objects. Let's make it green. You can see that they're matching, because this is the same font and the same size. And then we can check if the font of our figure is large enough or not. So in this case, it's a little bit smaller than 8 points, but it's also a different font. Now imagine if your figure is very large and you need to analyze the fonts that you're using there. You can use CorelDRAW to measure the space that you have for plotting. So let's create this rectangle here, and we know that our space goes from left to right like this. Let's move it here. So this is the width of the column space that we have for plotting. And imagine if your figure, let me just create a random figure. Imagine if your figure looks like this. So you need to adjust your figure to the plotting space. So what you can do, you can just take this rectangle. We know that it is exactly of the plotting space of the journal template. You put it here, and you make it as large as your new figure. You make it large like this. Now, you click on this text, and you remember it was 8 points. Now you can see that it becomes 10.6 points. This means that if working with this new larger figure and placing some fonts there, you need to place fonts of at least 10 points, so that when the figure is reduced to one column space, it will be reduced like this. The font will become 8 points. So this is an interesting test, an interesting adjustment that you can do to understand which fonts to use in your figures and how big should the elements in your figures be. As I said, there are many more features of vector graphics software that we can use to improve our figures, but we will discuss them in the future tutorials. And finally, one last thing that I want to cover, as I promised, is what to do if you have to work in Word, if you cannot work in LaTeX overlay. Then you cannot simply place your PDF images in a Word file. Let's see what we can do. So this is the same template of the paper, but now in Word. So you can see it's not LaTeX anymore. And we can see here the fields for figures. This is just a sample figure provided by IEEE, and you can see that it is pixelated, and we need to replace it with our new figure. So how can we do that? If we click here and we select Change Picture, there will be no option to select a PDF. So Word simply doesn't understand the PDF format. We need to select something else. And to do this, we need to save our image in CorelDRAW as SVG or EMF. So here you can see my folder, and we are trying to replace this standard figure with our visualization. And you can see that there is no PDF. So as I said, Word cannot read PDF files. That's why we need to use some other formats, and I already saved this example for YouTube Python in scalable vector graphics.svg. And if we select this SVG and say Insert, we get our figure, and it will be vector-based. Let's make it a little bit larger. And let's check that indeed it's a vector-based figure. So for this, I click on File, Export, Create PDF, and I'm saving this manuscript as a PDF file. Now let's open this PDF that we created in Word, and you can see that indeed this figure was pixelated, but this one, our new figure, is vector-based because we used SVG format when placing it in Word. And if your Word doesn't understand SVG formats, you can use another format called EMF, Enhanced Metafile. You can create EMF using CorelDRAW or other software, or if you don't have any software, you just have a beautiful figure in PDF, you can easily convert it using some online converters. So simply Google PDF to EMF and you will find some converters and you will be able to place your vector-based figure in Word without loss of quality. All right, so that's it. We have created a beautiful vector-based figure. We placed it in our manuscript. We adjusted multiple parameters and we also discussed how to modify it using vector graphics software and what to do if you can't work in LaTeX and you need to place your vector image in a Word format. I published all examples that we considered today in my code repository, so please feel free to check it out and use these examples and these plotting parameters. I also plan to finalize the manuscript, how to create beautiful figures, and publish it online later. Remember that you don't need to repeat my style. The goal of this tutorial is just to share my experience of how I'm tuning plotting parameters and some additional tips for data visualization. But eventually, in your works, in your papers, you will need to develop your own style. When working on your figures, you can now constantly think about all these plotting parameters that you can further optimize. For example, the plotting range, as we discussed how we can zoom out from our data set, the use of readable fonts, harmonious, good color schemes, etc. My goal for the next tutorial is to share more complex examples with you. Today we focused on a rather simple case visualizing a small data set, but in the next tutorials we can work on more complex and professional problems and use other visualization techniques. So here again I would appreciate your feedback. Please tell me in the comments which figures you would like me to work on and if you have any specific visualization problems you would like me to cover. Thank you for being with me through this long tutorial, and I hope that the ideas we discussed today will help you to produce very beautiful figures in your papers. Thank you and see you soon. Bye.